So what we've just seen is that reactions that have carbocation intermediates have the tendency or the possibility of carbocation rearrangements. So let's look at this example here. We're starting with this alkene and treating it with sulfuric acid and water. So the first thing to think about is that we know that when we see these conditions, all that is H3O+. So we're treating this alkene with H3O+, which is going to give us an alcohol. So this is a hydration. Let's go through a mechanism. I'm going to draw the mechanism up above here so that we can see what happens. So remember, in the presence of a strong acid, the first step in your mechanism is always going to be that something is going to get protonated, and that something that's getting protonated will be a weak base. Okay, when this alkene gets protonated, the carbocation forms, the positive charge forms on the more substituted alkene carbon. This is a secondary carbocation. Now remember, particularly in the case of secondary cations, you want to look for the potential for rearrangement, which happens here. So there's a hydride shift. And that gives us a new, more stable carbocation. This one is tertiary. And then what we can see is that given the product of the reaction down below, so the product right here, water attacks this carbocation, after which you lose a proton. I'm not going to draw that mechanistic step. You lose a proton. We've seen this in the previous examples of this hydration mechanism. That gets you to the product. Okay, so we have a product of a rearrangement. What if we did not want that to happen? That is to say, what if we wanted the product down here that I just circled in blue? So as you can see, this is a Markovnikov hydration, but no rearrangement occurred. So the OH group attached directly to the more substituted carbon from the alkene. So this is a Markovnikov hydration. But no rearrangement occurred. So if that's the product that we want, given the starting material alkene that we're using, we can't use conditions that would create carbocations because carbocations are vulnerable to rearrangement. So that means that we need to use an entirely different set of reaction conditions. The conditions that we use are called oxymercuration, demercuration. So this is introducing a completely new set of reagents that we haven't seen before, but it's going to get us the product of a Markovnikov hydration without the potential for rearrangement. So let's take note of a few important points here. So first of all, this is a hydration. We're adding the elements of water across the alkene and producing an alcohol just like we would in any hydration. In fact, we can be more specific. We can say it's a Markovnikov hydration. So for a Markovnikov hydration, it adds the elements of water across an alkene, producing an alcohol. And the other thing about a Markovnikov hydration, remember, is that the OH group attaches to the more substituted alkene. more substituted alkene carbon. Under these conditions, there are no carbocations formed in the mechanism, which we'll look at shortly, and no rearrangements. Now, there's a particular set of reagents that we're going to use to do this. So let's see what these are. So the first one, HgOAC2, this is called mercuric acetate. Okay, so the acetate ion. Let's focus in on that. The acetate ion is abbreviated AC capital O minus, or it could be OAC minus, and both of those mean the same thing, which is this structure here. So the acetate ion, remember, is a carboxylate, which is a conjugate base of a carboxylic acid. So acetate is the conjugate base of acetic acid. The other reagent is NaBH4. This is the formula for sodium borohydride. Now, the structure of sodium borohydride, we're going to have a sodium spectator ion, and the borohydride ion is a boron that has 4 hydrogens attached to it and a negative charge on the boron. Clean that up a little bit, like so. Now, between boron and hydrogen, it's actually hydrogen that's more electronegative. So each of the hydrogens has partial negative charge, which is kind of strange. This is not something that we've seen before. And the boron itself has a partial positive charge. But in this case, don't confuse these partial charges, which have to do with electron distribution, how the electrons are distributed in each of those boron-hydrogen bonds. Don't confuse those partial charges with the full negative charge. That's a formal charge, which is a bookkeeping device that has to do with the count of electrons around the boron compared to its valence number. Now, the final point that we want to make about this reaction, if we go back up here, notice that these reagents are numbered. That means that they're not all in the reaction mixture at the same time at the beginning of the reaction. So a final important point we can make here is that the numbering shows that the reagents are added into the reaction mixture in a particular sequence over time. They're not all in the reaction mixture in the beginning when you start the reaction. So the reagents, when they're numbered like this, are introduced into the reaction mixture in a particular sequence. So not all at once. Now we're going to see other examples of reactions both in this semester and next semester that follow that pattern as well. Okay, so what I mentioned was there are no carbocations in the reaction mechanism. So what does the mechanism look like? Well, we're going to look at part of it. We're going to look at some key parts. They're going to help you when you go to look at patterns, other patterns, so that you can recognize those patterns and be able to predict what happens. So let's use this as our example. So here's an alkene. In the first step, we're going to expose the alkene to mercuric acetate and water. And then in the second step, we're going to add in some sodium borohydride. The result, remember, is going to be a Markovnikov hydration product, so a Markovnikov alcohol, we could call this, meaning that the OH group has attached to the more substituted carbon. So I'm drawing in the OH and the H that were attached in the reaction. And remember, over at this carbon, there's another hydrogen that was already there. Okay, so the first part of the mechanism, we can think about the mercuric acetate as existing in the solution in an equilibrium with an acetate ion and HgOAc+. So what you have is a mercury ion, mercury 2+, that has two acetate ions attached to it. So it's an ionic compound. At any given point in time, one of those acetate ions could pop off, and then it can pop back on, it can pop off, and then pop back on. Okay, so this is what this equilibrium is. So somehow, in all of this, and people draw this differently, so I'm not going to show you one way to draw it, because there's different ways that you can envision this. But somehow, the alkene becomes associated with HgOAc+. Now again, there's different ways to show how that association can occur. And so we're not going to worry about that. We're just going to look at what the result is. When that happens, you're going to get the following. So here's the carbon skeleton of the alkene that we started with. The alkene pi electrons have become associated with the mercury, which still has an acetate group attached to it, and has a positive charge. This intermediate is called a mercurinium ion. Remember that when you see IUM, that typically is telling you that there's a positive charge associated with the structure it's describing. The mercurinium ion, just like the alkene, has a more substituted carbon and a less substituted carbon. So I've tracked those carbons from the alkene to the mercurinium ion that's formed. Still in the first step, we also have water. Water is going to function as the nucleophile. And it's going to attack the more substituted carbon in that little three-membered ring. That's going to cause the ring to open. So let's make a note of what I'm about to show you, and then we'll look at the mechanistic arrows. The nucleophile, in this case, is water. So it's the thing that's supplying electron density. It's going to attack the more substituted ring carbon, and the consequence of that is that the ring is going to open. So if we look at what we have a three-membered ring with two carbon atoms and something else that's not carbon. We can call that a heteroatom because it's not carbon. And that's a three-membered ring, so there's a particular amount of strain associated with it. So what's going to happen is that the water molecule, using a lone pair from the oxygen, is going to attack and form a bond with the more substituted carbon. If we stopped drawing right now, that would mean that the carbon that I've highlighted as yellow, the more substituted ring carbon, would have too many bonds to it. So something has to move away. A pair of electrons has to move away from that carbon so that it doesn't exceed the octet rule. And the pair that moves away is the pair that links that carbon to the mercury. So what does the result of those arrows look like? So the water molecule attached to the more substituted carbon, that was the one that I highlighted as yellow. The more substituted carbon was connected to the less substituted carbon, which had a methyl group coming off of it. The oxygen now has a positive charge. And notice in the mechanism directly above and to the right, the bond broke between the yellow carbon and the mercury, but the bond between the pink carbon and the mercury is still intact. The acetate that was attached to the mercury comes along for the ride. Because the mercury accepted a pair of electrons, it now has no charge. Now, what we've seen in the past, when water attacks, for example, a carbocation, you end up with this structure, and then you have to pull a proton off of it to get the neutral OH group. So that's going to happen here as well. So we can draw, for example, a water molecule, or it could be an acetate ion that would accept this proton. So you'll see this drawn using different bases that are present in solution. So it could be water, it could be acetate, and that's going to get us to here. That takes us through the first step, the one labeled 1, up above here. So now to get to the product, in the second step, we're going to introduce into the reaction mixture some sodium borohydride. Now this is the step that we're not going to show a mechanism for. But what you should know is that the sodium borohydride is going to replace HgOAc with a hydrogen. And so the bond that ends up breaking is going to be this one right here that I just drew the little orange squiggly line across. And that gives us the product of the reaction. The hydrogen that I've highlighted in blue is one of two hydrogens at that carbon atom. And that's the one that came from sodium borohydride. Now the pattern that we saw up above with the mercurinium ion, you're going to see again. And so what you're looking to recognize is a three-membered ring that has two carbons and another atom that's not carbon. That's called a heteroatom. So a heteroatom is an atom that's not carbon. There's going to be a positive charge associated with that ring. And the ring carbons, the carbons that are involved in making that little three-membered ring, will be unequally substituted. So you'll have a more substituted and a less substituted one. So anytime you have this exact pattern, the nucleophile will always attack at the more substituted ring carbon. In this example, that's going to be that carbon right there. Okay, so now we know that we can make a Markovnikov alcohol without worrying about rearrangements. We should just use oxymercuration demercuration, which is the name of the set of conditions that we've just been looking at. Now there's another way that we can extend the idea of hydration. So using oxymercuration demercuration as a starting point, let's turn our attention to alkoxymercuration demercuration. Now, the reaction mechanism is exactly the same. It's identical to what we just saw. The only difference is that instead of using water with the mercuric acetate in the first step, you're going to use an alcohol instead. And so the difference is going to result in you making an ether as the product instead of an alcohol, which we did a few minutes ago. So generally, OR is called an alkoxy group. And so this is why we're calling the reaction alkoxymercuration instead of oxymercuration. So let's use this example and draw in a mechanism. Now, I didn't leave myself very much room, so I'm going to draw this right here, and then we'll work out the details later. So we're not going to draw lots and lots of arrows. Just remember that when you introduce an alkene to mercuric acetate, the first thing that happens to it is a mercurinium ion forms. Like so. Now in the present example, we don't have any water. If we did, it would be explicitly written. What we do have is an alcohol. So I'm going to keep it abbreviated, but remember, this could be something, the R could be a methyl group, so this could be methanol, it could be ethanol, it could be isopropanol, what have you. So we have some alcohol. The alcohol at this stage is going to act exactly the same way that we saw the water act. We have that three-membered ring pattern. Two atoms that are carbon, one that's not, positive charge. And so the nucleophile is going to attack at the more substituted ring carbon. So that opens the ring. And gives us this intermediate. So now I'm going to actually redraw this a little bit to get this sort of a little clearer. So now, instead of having two protons attached to that oxygen, there's only one. And so that's going to be the one that gets removed. Now, the first time we saw the mechanism for oxymercuration, demercuration, that is on the previous page, we used water to remove this proton. You could also use acetate. And the same is true here. You could use acetate, but there is no water. We do have alcohol, and so another alcohol molecule is going to end up removing that proton. So that gets us to here. Again, completely analogous to what we saw in the example with water. And then sodium borohydride is going to replace the HGOAC group with a hydrogen. Okay. So hopefully what you can see is that the pattern that's followed is exactly the same. Any place we had water, now we have alcohol, and so the alcohol is going to do exactly what the water would have done. So this brings up an important point that's going to be useful to us going forward. And that is that water and alcohols are very similar chemically. So what we've seen so far with water and alcohols, we started looking at this in the context of acid-base chemistry. And what we saw there was that water and alcohols are both weak acids and weak bases. So they're both weak acids and weak bases, but they're also both weak nucleophiles. So what we can say is that they have comparable nucleophilicity. Now, the nice thing about this chemical similarity is that if you can remember that they're weak in pretty much all respects, they're weakly acidic, they're weakly basic, and they're weakly nucleophilic. So what does it mean when something is a weak nucleophile? Nucleophilicity is a measure of how fast something reacts as a nucleophile. So something that's a weak nucleophile compared to a stronger nucleophile is going to react more slowly. So nucleophilicity is how fast something reacts as a nucleophile. So understanding the chemical similarity of water and alcohols means that in most cases, anytime you have a molecule of water in a reaction, an alcohol could do exactly the same thing that the water molecule could do, and vice versa. So let's take this back to what we did initially with hydration, which was to do a Markovnikov hydration using water and a catalytic acid, like sulfuric acid or tosic acid or nitric acid, with an alkene. If instead we used an alcohol, it's going to follow a very similar pattern. So let's look at this example. Here's an alkene. So remember, treating this with sulfuric acid and water gives us a Markovnikov alcohol. Now what we know about this is that if we have sulfuric acid and water, we have H3O+. If we change up the conditions a little bit, so we'll use the same alkene, but this time we're going to use sulfuric acid in methanol. So an alcohol instead of water. Notice that there's no water explicitly written in the reaction conditions. And it's not being produced in the reaction either. So you have no water here. This is important to recognize, because oftentimes, because water is so familiar, people like to invoke it and suddenly have it appear in a mechanism or in a reaction where it's not really in existence. So be careful about that. Okay, so sulfuric acid and water means you have H3O+. But sulfuric acid and methanol means you have ROH2+, which in this case is protonated methanol. Okay, so what's going to happen here? Well, in the first step, the alkene will be protonated in the fashion that we saw with the hydration mechanism. So it's going to accept a proton, which goes on to the less substituted alkene carbon. So let's just keep track of where that proton goes. So same as before, remember there's also another proton on that carbon. I'm not drawing it in. I just want to show or remind you where the proton goes. And the carbocation, of course, forms on the more substituted alkene carbon. At this point, remember, there is no water in your reaction mixture. But there is methanol, which is going to behave exactly the same as the water would have. So the methanol attacks. We get this intermediate. And then just like water would have done, a proton is removed by a methanol molecule, and that gives us a neutral product. So the product here is an ether, and we got to it by adding the elements of an alcohol across the double bond. So the elements of ROH across the alkene. Okay, so the take-home message from this page is that any place you have water in a reaction, an alcohol is going to participate in the same way that the water would have. So water and alcohols, both are weak acids, both are weak bases, both are weak nucleophiles. They're chemically very similar to one another.